Okay, a couple quick reminders. Welcome back to Monday, week 2. So today, 3 to 4 o'clock in chemistry, D215. That's the drop-in for my time today. That's my office hours at this point, just in class. Again, bring any problems at that point. There's nothing else we're going to cover in that time that we do not, based on not bringing material to this. This is something where it's your time to bring problems for me to help work through. If you're interested in just coming and listening to other questions, that's fine, but I will not be bringing other extra problems to that point. This is something where I need you guys to come and interact. TA tutorials will be tomorrow, Tuesday, from 11:30 to 12:30 in D215. 315? 213, excuse me. So that was announced up. I know it showed up on Piazza, but I'll post that one up as well. So 213 during that time is the tutorials at that point. Also make sure that you're on Piazza. A couple quick things I want to go over for housekeeping. A couple questions people brought up. So remember, what I want to do is I'll be posting preview slides, which is basically the same stuff we're going to talk through in class, minus some of your problems, minus some of other things like the fully drawn mechanism. This is stuff for you to bring in class, so you've got a good copy of something to write on and add your own notes to, right? So you're not constantly recapping slides yourself. After the slides, or after class, I will take the exact slides you see here in class as a PDF and post it, which means you don't have to feel like if there's a question that comes up here, you got to whip out your phone or your iPad and take a picture of it because it only exists in that 30 or 40 seconds. Everything that I show you up here will be posted as a PDF, no holdbacks. Okay, so that means that you should feel confident that anything you have here, if you can't transcribe it or write it down, don't freak out, you will have it after. Also, I've got the lecture recordings. These are the real recordings of what happens here. This is not another year. That's not another forgiving. This is the same run of show of what you see in class. So all the marks and everything else that I do here in class will be on those slides. I will not be posting 3 sets of PDFs of my preview, my post, and the notes. So if you want to go back and review what gets written down, go check the lecture recordings. The screenshots are all there. All the notations are there. If you want to study in advance, go check the preview version. Use those preview ones here in class. The post ones will have everything else that you can annotate or add to, but that's all the other components, right? That's the goal of what I'm trying to go through. And again, the reason why is in previous years when I've had 3 of these slide decks, people start trying to manage 3 different PDF decks on top of each other with a lot of duplication. It gets very confusing. So I'm trying to kind of consolidate it where we only have the final lecture slides after the class and the lecture recordings for other components. Anything else that we put up as a practice, try it later, I will do that as a pencast in the end of that lecture and attend it to the end of the YouTube one. So if you want to see how this is done, try it yourself, go back, go watch that part of the lecture. That's where that solution will. I won't be excising that as a separate component because it's meant to be a work problem, right? I'm meant to talk you through how this is done rather than here are the arrows, go look at the answer, right? Any other questions on that? Okay, other content. Boop. So we have the recommended questions right now for Brown. We have the recommended questions from Volhard. Both of those ones are up in that point. If you want to check your answers in that point, there are solution manuals from both of them. This is not my content. I can't give you that answers for free. That is stuff that they have curated. If you have questions around this, post it on Piazza, ask classmates, ask TAs, bring it to me. I can work the problem with you, but I can't just post the solution manual for these materials. That's stuff from those textbooks. Legacy problem sets are now up on Canvas. So this is every problem set from 213 from the last 2 years previous. Now again, asterisks. These correspond to chapter numbers from the original Brown book. So some of the chapter naming is different, but the content is the same. The only other one I want to flag is these are legacy problem sets going back from David Perrin, which have a lot of other content that we have now removed from the class. So there's reactions that he goes into there like ozonation and other ones that we don't focus on now in class. So some of those problems will look obtrusively hard or impossible because it's not material we're covering here in class. They're still good practice problems, but if you cannot do these and you're like, what the heck is going on? I have never seen this before. You are correct. And that is something that, again, I can't handle or can't clarify now. We're building these new problem sets as we go through. I will get them online as soon as I can. You'll have them plenty of time for the midterms. Sample midterms will go up closer to the actual exam. I will be posting 4 or 5 different versions of the midterm, including last year's midterm, for you guys to practice with too, with the actual answers. And I'll usually post them in staggered. I'll give you the midterms, no answer key. I want you guys to try them first without having the temptation of going and saying, question 1, look at the answer key. Yeah, I probably would have got that. It's meant for you to do this another live fire thing to work out your timing, work out your skill for that point, work out working with these problems. And again, their level of difficulty, which is what you're going to have to do here in class. Any other questions? Yeah?
For the new problem sets, are we talking that they will be released within like days or weeks?
As fast as I can. If you have, here, actually on that point, if you want more content quicker, I will give you the email address of our department head, and please ask her to remove things from my schedule so I can do more of this part. No, like seriously, I can show you my schedule if you'd like. But yeah, it's, again, as fast as I can. The purpose of these is really I am generating content. This here, your sample midterms, and this should be more than enough for your preparation. This is just more stuff for you to practice through. And the thing I'm really trying to build is like we do here in class. There's kind of crawl, walk, run. And making that kind of problem set where you've got those connections built in just takes me time. So apologies doing it live. OK. Last class, aldehydes and ketones. And we introduced you guys to hemiacetals, hemiketals, acetals and ketals, and the mechanism behind them. Really, really important thing of these reactions. Are they driven by kinetics or thermodynamics? Everybody says in one creepy voice it is. Why? How do you know it's thermodynamically driven? What do we do to really push acetal-ketal formation? We use the Chatelier. More of a starting material will push it to product. Removal of water. These are not kinetically driven reactions because when we talk about stability, we're either on an isoenergetic surface, in other words, going from ketones to acetals, we're not gaining a lot of energy or losing energy. In fact, we're probably climbing uphill. So the way we get to those products that are less stable is we do a reaction with excess starting material, pushing that equilibrium, and then we remove all the other stuff that could allow it to go backwards. I remove the catalyst, and I trap it in that state. So we allow these reactions to go forward mainly by thermodynamic features. We talked about aldehyde does a single step to the acetal, which then goes to your hemiacetal to acetal. Ketone becomes hemiketal to ketal. Now this is under acid conditions specifically. When we're using acid conditions, we can get these 2 steps. A mechanism that allows you to do base catalyzed. Base catalysis can get you this far. Base catalysis will not allow you to go to the full one. If you look at the mechanism, that should become apparent to you. It's a problem we're going to look at in more detail. But that's a really key thing. If you're making ketal and acetals, these are acid catalyzed conditions, not base catalyzed. If you're doing hemiacetal, hemiketal, acid and base are both possible. OK, review time. Take a second. Think about this one. We're going to do this one lightning round. So you have 30 seconds on your own. Come up to a decision. Which side, left or right, is favored? OK, turn to the person next to you. Why are you right? Why are they wrong? 30 seconds, go. Okay. And time. All right, show of hands. Starting material is favored. Why is my voice cracking? Starting material is favored. Product is favored. Why? PKA. The product is favored because of pKa. More words, please. Yes?
The pKa of the acid product, or the acid compound on the left is lower, so therefore it is stronger, so it will be, the dissociation of it will be favored.
Right. If you're looking at this, you've been given two molecules, and you have to find the acid on the starting material, acid on the product. The pKa relates to how strong of an acid it is. Remember, what did we talk about pKa? Strong acids have what? High or low pKas. Acids have low pKas. -4 beats 9. That is a stronger acid, which is going to push the equilibrium that direction. Remember, everything on this side is the stronger. And remember, that suffix matters, ER, because we're talking about some things in some cases. Strong acids, you'd say, oh, HCl, sulfuric acid. Stronger acid means in an equilibrium like this, one is winning over the other. That can sometimes mean terrible and really, really, really terrible. It's a relative value. But that means this is my stronger acid, that's my stronger base, which gets this one as my weaker base and my weaker acid. So yes, the equilibrium lies in favor of that side. The carbonyl thing, positively charged oxygens like this are very acidic. Think of them like the hydronium ion, right? H3O+. Okay, next question. What do you need to make up this molecule? Quick thing before we get going, what does that arrow mean? Retrosynthesis. This is not being stylized of like, oh, it's a synthesis, but I'm really cool, so I'm opening it. No, you're talking about sort of the opposite direction. I'm saying I make this molecule from something else. Okay, turn to the person next to you. How would you make this molecule? What reactions or reagents are needed to make this? Okay, time. So, the way I usually work on these questions, you start off, if you've asked to do a retrosynthesis, you redraw the problem where that is your product, right? So this is your target now, which means you're filling in the species you need on the left hand of the equilibrium, or left hand of the equation to make this compound. Okay. The reason I've broken it down like this is if you look at this, what kind of molecule is this? We had it named last time. We gave this new functional group. This is called a ketal, right? I'm focusing on this center with two oxygens attached to it and the stuff in the middle. That's my ketal functional group. We make ketals by breaking those carbon-oxygen bonds. That's why I've highlighted those two under different colors, which makes this chunk here and this chunk here, those symmetric parts, those are part of my starting materials. What group or what molecule do I need to get those two chunks? This here came from what? Yeah, ethanol or an alcohol. Basically, if I broke this bond here and here, then that would have to come from OH and HO. It's symmetric. I have two molecules of ethanol in this case. That's the first piece I need. Times 2. Okay, that means I got the stuff in the middle. Notice here, I have a carbon that is attached to two oxygens. That is the carbonyl piece of what I'm actually trying to build, right? So what does that molecule look like? This part right here? Yeah, that's acetone. It's a ketone because we made a ketal. It's going to be a carbonyl in the middle that has two different carbons on either side. Most important thing to focus with these, how many carbon-oxygen bonds do I have right here? 2. How many carbon-oxygen bonds do I have right here? Also 2. That helps you identify where the carbonyl was. It's now masked. This carbonyl center here is what we're dealing with. It is not that. It is not that. Those two are my alcohol centers. Those only have a single carbon-oxygen bond. Those are the alcohol fragments. Whatever carbon is still attaching 2 carbon oxygens, this carbon here is holding 2 carbon oxygens, that is my carbonyl. All right, that's it. What else do I need for conditions? How do I stitch these together? Acid, not base. So I'm going to choose an acid. I'll use HCl catalytically in, anybody guess a solvent? What do I want to do in here? Ethanol is a pretty good choice, right? Because that means I've got a buttload of ethanol. Could I do this in water? Why not? Water is a product of what I'm trying to do. Water is a bad choice for me to try and do this reaction. The other thing you could potentially do, give me one other thing besides ethanol that might allow you to do this reaction. What's a solvent, not ethanol, would you maybe choose? Think back to 123, 203. Would hexane work? A apolar, aprotic solvent like benzene, hexane. Good choice, bad choice? This is a concept of like goes with like. If we're taking something like acetone, ethanol, HCl, these are all polar molecules. We do not want to use something like methanol. What would happen if I tried to use methanol as a solvent? That's polar. But what would happen now? Yeah, I've got another alcohol coming up to the party. If I'm trying to put in ethanol and I run it in methanol, probability says that other alcohol is going to win. So I need something that's polar, but alcohols are a really bad choice. Amines, anything that's a heteroatom H is a bad choice. Another solvent you could use might be, let's say, THF. Polar aprotic solvents might be good choices to use here. You're still going to have to use a whole bunch of extra ethanol. Stoichiometry is still going to help you, but that's the only other choice for you to kind of potentially go to this. Do not use other alcohols. Any other questions? Yeah? Oh, you could. What would happen, though? What do you think happens with that? If you use acetone as a solvent, good question. So the defense has submitted that acetone can be used for this reaction. Does anybody want a prosecution? Yeah? Well, it could evaporate. That's one. But, you know, these are all volatile as it is. Evaporation is probably not the thing that worries me in this case. You're not wrong. Like, acetone would work. But there's a strategy perspective of this one. This is what you'll start to see. Most of the time when we're doing these reactions, the thing that I want you to put your eyes on, and in fact, you'll start to see this more and more, is when we run reactions, there's kind of like, yes, there's 2 components, but one of them is the star. The molecule that we want to put emphasis and focus on is usually the functional group that we really care about. And then typically for these reactions, the carbonyl is the business end of the molecule. That's the thing we want to care about. Ethanol is the partner, but secondary character. If this was K-pop, that's the second leading male. Not coming away with anything that's cool at the end of that one. The carbonyl is the one that's a business player because the molecule you want still has a carbonyl in it. So what you'll start to see, typically, there's nothing wrong with doing that. But what you'll see is a pattern. The carbonyl is the main player. The acetal-ketal is the main player. The alcohol is the one that you're going to use excess on. Because usually what you'll start to see is the alcohol piece of it is the stuff that we've got in bountiful excess, and we can use it up. So this is typically what you're going to need in terms of the stoichiometry. You need trace acid. We just discussed a little bit more about the practicalities of this reaction. Okay, so this class, we're talking about protecting groups. And this is where that thing I just mentioned is really important. You can use protecting groups to deal with the carbonyls. What we're doing here is we're using the alcohol as a way of borrowing reactivity or protecting a carbonyl. So look at these structures. We're under acidic conditions. If I start off with aldehyde or a ketone with these guys, what happens here? You form a ketal or an acetal, right? Because what you've got in terms of makeup, right, for making these reactions work, to make these reactions work, I need a carbonyl, check. Acid catalyst, check. And 1, 2 alcohols. You've just got them both in the same molecule. This is where what we call cyclic acetals or cyclic ketals. So what will happen here is the first case, I'm going to make that carbonyl, so I've got my R and my carbonyl center. I'm going to make an acetal, except now I've got my 2 oxygens attached like this. And that corresponds to 1, 2, 3, 4 is my 1, 2, 3, 4. My carbonyl center right here is that center right here. And to finish it off, I've got a hydrogen. So this is a cyclic acetal. On the bottom, same thing. Cyclic ketal would just be 2 R groups, R prime, attaching to oxygen, oxygen here, where again, 1, 2, 3, 4 is 1, 2, 3, 4, where the 5th bond or the 5th center is the carbonyl center. So this is really convenient. What this allows me to do is take one molecule and one molecule and fuse the 2 together. The mechanism is the same. What will happen is 1/2 of this reaction is going to react. One of the two oxygen centers from over here will react first to make a hemiacetal or hemiketal. But then, under these conditions, you've still got this extra pendant alcohol along. That first oxygen addition now has this other alcohol nearby, allows me to form a ring. Except we're forming a ring now with that other species. So one of these will go in first. I get a hemiacetal or a hemiketal. This other oxygen will close in, and I get my final molecule. What do you think happens with these? If you had to sort of guess about these in terms of stability, more stable or less stable than the acyclic compounds? These are much more stable. This has to do with both stoichiometry and concentration. When I add these 2 pieces together, this oxygen is right there. It's nearby, which allows that second reaction to be catalyzed. It's basically faster because I've got another oxygen ready to go join the party because it's part of the actual system. Instead of waiting for another oxygen to float in from another part of the reaction, it's actually attached to the same molecule. So what I can get from here are these cyclic acetals and cyclic ketals. And these in general are more stable than their acyclic components. These are the common diols that we use to make these cyclic structures. And what you'll notice is I've got a 4-membered system plus the carbonyl equals a 5-membered cyclic structure. This is a 5-membered piece, oxygen, 3 carbons, oxygen. That gives me a 6-membered structure. This here is an oxygen sulfur. Remember, sulfur and oxygen, they're cousins of each other. They're right under each other in terms of their bond order and relative nucleophilicity. Sulfur is actually much better than oxygen, but they behave in a similar way. Thiols and alcohols are cousins to each other. I can take molecules like this. How big is this ring that I form according to that guy here? I've got 1, 2, 3, 4, 5. Carbonyl equals 6. That's a 6-membered ring. Difference here is I've got these 2 methyls on the backbone. That does what's called Thorpe-Ingold. Basically, taking these 2 methyls, it by sterics forces those 2 oxygens over into one side. It holds down a certain geometry, which looks like what we need to make our ring. This here is going to push those oxygens over to be in that kind of enforced geometry. This one here, 1, 2, 3, 4, and the carbonyl would be 5. This is what we call a catechol. These are aromatic rings where it's actually rigidly pinned in that diol. And same thing here, all this extra bulk here allows these 2 oxygens to usually sit in a geometry like this. OH, OH. So it's enforcing this geometry which allows that formation of these cyclic structures there. So we're moving through and they're adding sterics. These are the pieces that you're going to use when you actually start to do protecting group chemistries. So just quickly, it's just a reminder of how energies work. And remember, when I'm talking about these structures, we're talking about in these reactions, these are primarily thermodynamically driven. As we go through these pieces, though, the thing I want you to focus on is remember, there's 2 ways to influence reactivity. I can either change the relative stability of my starting materials or the relative stability of my products. Both of those 2 things will impact whatever equilibrium I'm dealing with. So this allows me to go through and identify 2 different factors to help push a reaction in terms of favored or unfavored. In general, we're looking for ways to minimize energy. So if I start from a high energy compound, I'm trying to go downhill in some species. in the end, if you actually look at this, what are the things that help to influence how stable something is? Starting material or product. Think back. We talked about this a little bit. What is something that stabilizes a molecule? Any of the features. And again, you can go back to like how we did pKa's. Yeah. Yeah, resonance, conjugation, those make things more stable. And again, that means making something stable we're not talking about starting material or product. That's just a feature of a material that can influence the relative reactivity. So if something has resonance to start off with, it's more stable than something else. That's a more stable starting material. If you're making a product that has resonance, that's a more stable product. So resonance is one. What else? Think back to, again, pKa's. What's something that maybe helps a negative charge? Yeah. Polarizability is a good one, right? Because they are allowing to delocalize that charge. What else? Inductive effects, right? So that's electronegativity, tugging on that thing, which can either stabilize or destabilize. Things like electronegativity really matter because we have two directions, right? I can stabilize negative charges. I will also conversely destabilize positive charges. Resonance helps charge in general. Positives and negatives, resonance will help them out. Right, so these are those factors. So based on those, rank these. Who do you think is more reactive? Who do you think is least reactive? So this is partly an exercise for how you should attack these kinds of problems. Somebody give me a strategy. You have 4 molecules on the board. What you should probably do is group them. Yeah. Okay, you can look for resonance. Sure, which one has resonance or has resonance associated? Yeah, this one's got resonance. Sure. But if you had to group these, yeah. There you go. A good first step. If you're given 4 molecules, 5 molecules, break them into common groups, which is based on common functional groups or common reactivities. So I would say aldehyde versus ketone is a really good first split. So first guy here, this is which team? Team aldehyde or team ketone? That's team ketone. Next one is aldehyde. Next is ketone. And then aldehyde. Reason why? Aldehydes are more reactive than ketones. We talked about this class 2, class 3, right? That delineation matters the most. Aldehydes versus ketone is your first cut. So what you've just done is you've stratified it. I no longer am trying to rank 1 versus 2 or 1 versus 4. I can now split them into 2 binary comparisons. Aldehyde versus aldehyde, ketone versus ketone. All the aldehydes will win before all the ketones. We'll start with that. Okay, so now we've got 2 aldehydes and we say they are more reactive. Which one wins? Aldehyde 1 in the kind of space 2 versus aldehyde 4. 2 versus 4, who do you think wins? Okay, we got 1 vote for 4. Any votes for 2? Why does 4 win? I agree, 4 wins. Why?
Because it's got less hyperconjugation because at the carbon that is attached to the alpha carbon, there's only one other.
Okay, yeah, you're going with a hyperconjugation argument. So you're saying this is my carbonyl center. I have hyperconjugation out here, and you're trying to say, okay, maybe there's more other carbons and stuff. In fact, I think that's probably equal. Remember, hyperconjugation is talking about sigma bonds at the center alpha. And there are 1, 2 hydrogens and a carbon, versus here I just have 2 carbons and a hydrogen. There's basically the same content of sigma bonds nearby. Yes, carbon-carbon versus carbon-hydrogen, but remember, hyperconjugation is kind of a local effect. We're not really getting much hyperconjugation from this part of the ring. It's really what's immediately attaching to that center right here. It's the nearby guy. So a little bit, but there's something else. Why might the ring and everything else hurt? Sterics. I'm a big honking ring. I'm not letting anybody nearby. This center here is partly shielded. So reactivity favors both the electronics and the lack of stabilization or sterics. So this guy, oops, that's going to be number 1, which means second aldehyde is number 2. Okay, now you've got 2 ketones. Ketone 1 versus ketone 3. Which one is more reactive? Ketone? Ketone 1. Why?
As for ketone 3, the reason why it's less stable is because of sterics and resonance.
Sterics and resonance. Resonance being the big one that's probably going to help you here. There's two reasons why sterics are a little lighter. First of all, resonance is a massive impact in terms of stability. If you can use it, it is great. It has a whole order of stability better. Second, too, the aromatic group, phenyl like that, is a plate. It's a sheet, which means you can kind of get it out of the way pretty easily. It does have steric impact, not nearly as much as sort of like the sp3 kind of centers. So yeah, that'll be number 4 across this. Good job. So what this lets you do is look at more complex molecules like this and break them down. So same rules. Which one is most reactive? Which is least reactive? So we got to vote for that one as number 1. Anyone want to back that one up?
Yeah, I was just going to say probably that one because it's like the least steric inhibitor, and there's also resonance.
Resonance where?
There's no resonance on that top one.
Yeah, good call. Exactly. Sterically, I'm with you. Steric says this one is out and away from the molecule, right? Everything else is kind of condensed into a ring. Second one, too, down here, I've got resonance nearby this. So that's probably going to put this last one probably in last place. I'm going to say that that one is probably my least reactive because it's a carbonyl. First of all, if you look at these, can I make the aldehyde versus ketone split? No, they're all ketones. So that's out. Next, which ketones are accessible? Yeah, guy in the top, that one wins. 3, that's definitely going to be last. That's just because of resonance. Occam's razor says this is going to be somewhere in the middle, right? It's going to be something that's less reactive than the other two just because it's part of a ring. It's part of embedded into a thing. So sterics is going to make that one hindered. This is the kind of strategy you started working through. And more importantly, you have to start looking at molecules as constituent parts. So instead of just 2 molecules, left versus right, you can use the same rules to look at different functional groups, common function groups, in the same molecule, right? So we're doing the same comparisons we did over here in this last example. We're just doing them as constituent parts of the same molecule. Yeah? Why is this more stable or less reactive than this? Sterics. If I'm an aldehyde, I'm more reactive than a ketone. But if I'm an aldehyde that has a steric, something that's shielding it, it's harder for me to react. My transition state is higher, effectively. That's what makes it more stable in that case. It's less about a thermodynamic effect. It's more about it's harder for me to get my nucleophile to approach that center just because I've got shielding that makes it. Think of it just like an SN2 reaction. Primary alkyl halides react faster than secondary alkyl halides because of sterics. Yeah? It's not a lot, I'll give you that, but it's enough to make a split between the two. I'd say that either and that's why both aldehydes lap the ketones for sure. If you have to choose amongst the two, having less sterics nearby, it will still be the only way you can differentiate between the two. You're right, it's not going to be a ton, but it's enough, right? I'm saying that there is a, call it a small difference in energy between the two. It's the only thing you have to differentiate them, right? Okay. Main one to focus here is the rules that you guys apply in these individual molecule by molecule can be applied by the aggregates. Yes?
I have also a question about the last slide.
Yes?
If the second one is a cyclohexane, if it was a benzene ring, would it be more stable than the first one?
You like making nightmare problems. Okay, the question is, what if you did that? So what you're trying to set up is the aldehyde versus ketone fight. Okay. First of all, that is what I would call trying to limit my swearing in class, not a very good move. In general, right? So you're right on it. Now what you've got is aldehyde versus aldehyde with resonance compared to ketone without resonance and ketone with resonance. this gets a lot harder, right? And because it's really going to come down to nuance. So I would look at a question like this and say, not fair game, right? I'm not trying to get you guys to compare apples to oranges, but let's play hypothesis. What if I gave you this as a question and I gave you the result? If I told you I take the aldehyde on the left, number 4, so I'm going to take this molecule, and this molecule. And I tell you that in that case where I've got 1, 2, 3, and I were to run a reaction, and that one works and this one works, but this one is slowest, what can you now conclude? If I tell you the result of the reaction, not telling you to predict it, but if I told you, if you've got that, and this ketone reacts, and this one just sits there and does nothing, now you can conclude something. The aromaticity of that aldehyde knocked it below the reactivity of the ketone. It's inverted those two, right? But I would generally, not fair game to go, can you compare between these two? That's a memory game. But if I give you the components to solve it yourself, you should be able to understand what I'm telling you based on a reaction outcome. Make sense? Again, that's my Scout's honor. I will absolutely try my best. Sometimes it doesn't show up. I'm sorry in advance. Any other questions? Okay. So this is where we get to use this relative reactivity and the cyclic acetal formation, what we call protecting groups. Protecting groups are important because it allows us to do reactions and temporarily, this is the Harry Potter sort of invisibility cloak, what we can do is basically take a carbonyl and make it not a carbonyl for some period of time. What makes a carbonyl work for most reactions, Grignard addition, is because it has a carbon-oxygen pi bond. I can temporarily remove the carbon-oxygen pi bond. So I can use this equilibrium nature to form acetals on demand or form ketals on demand, and then later do my deprotection. This is where having this as a reversible reaction using Le Chatelier means I can go back and forth in this equilibrium and use it as I need. So if I have a molecule with a carbonyl, I can temporarily install this cyclic acetal using catalytic acid, strip out the water, Le Chatelier, and then when I'm done, I can do a whole bunch of other chemistry over here that might actually react with that carbonyl. If there was something like an aryl halide or an acid halide, I can now go through and protect my carbonyl compound, then go do chemistry in this part, and then all I have to do to deprotect it is add water, add a catalytic acid, strip out the alcohol, and run the reaction backwards, re-expose the carbonyl. So it says in this general point, if you're using protecting groups, every protecting group adds a protection step, the reaction you want, and a deprotection step. It's the synthetic walls. See, the people at home that are just watching the videos, they don't get this kind of, in class. Wonderful. But my point is, you have to do this 1, 2, 3, 1, 2, 3. That sequence is super important because it lets us do the impossible. If I had to make this transformation here, and I've said that it's going to be a Grignard, look at the components here. I'm starting out with alkyl halide. That's a what? What's that functional group? Aldehyde. This is a what kind of bromide? Primary, secondary, or tertiary? Primary bromide. This is what kind of functional group? Which aldehyde is more reactive in this sense? Aldehyde 1 or aldehyde 2? Aldehyde 1. Why? Yeah, I've got stability, aromaticity. This is my more reactive aldehyde. If you look at this transformation, I can probably, if you kind of follow through, you should be able to see that chunk there is this chunk here, which makes this bit, right? That carbonyl center is that one right there. That's the bits and pieces of this reaction, which means the bond I just formed is this one. I could do this by a Grignard reaction, right? I'm taking the negatively charged center here and adding to this carbonyl. If I had to just make a Grignard here, and I've got this aldehyde, this will just eat itself. Because the Grignard, I can take that alkyl halide. I can take magnesium. If I made a Grignard and I leave that more reactive aldehyde together, That is just going to react with itself. So what I need to do is the protecting group waltz. I start off with a reactive aldehyde. I take my cyclic acetal, this dial, I do my acetal formation, and I install a protecting group. That carbonyl is no longer a carbonyl. And remember, how do I strip out? How do I break down my acetals? Acetals are formed using acid, stripping out the water, and I use acid catalysis to form them. If I was going to break them down, I need acid catalysis, water to strip them down. They are actually stable to base and other nucleophiles, which means I can do my Grignard reaction, form my Grignard reagent. I now do my nucleophilic addition to that center to form this species where my protecting group is still in place. Then I do a deprotection step. I'm cutting out this group by adding water to the system and re-exposing my aldehyde. So this is the warp speed move, right? What I can do is I can actually temporarily protect that aldehyde carbonyl. I start off with a more reactive aldehyde, I create an acetal, then I do my Grignard reagent, keep the protecting group in place, cutting it out to re-expose my component. So I have this protection, reaction, deprotection sequence. So this is where you need to understand or remember your relative reactivities. You need protecting groups if you're trying to react at the less reactive center. I can use the protecting group to carve out or protect one compound, do the reaction I want somewhere else, and then deprotect it after. So does that make sense? Yeah?
Would you have to isolate the compound on the left? You can do it with both, even though there's aromaticity on the left.
Oh, yeah. This is where make your life easier, man. If you want to make this compound, don't put both of these in the same flask at the same time. That will help. There are some cases where the molecule has both, in which case that's where I have no choice. I have to carefully react with one, not the other. But in a case where I could choose to do them sequentially and just not add the confounding reagent, that's a better way to do it, for sure. Yes? TFA. Who knows TFA? You should know that that three-letter acronym. TFA stands for... Oh, really? Okay, sorry. TFA. Trifluoroacetic. Or trifluoroacetic acid. It looks like carboxylic acid with 3 fluorines on here. Oops. Fluorine, fluorine, fluorine. Think of it like acetic acid on steroids. This is about as dangerous as you're going to get and way stronger than a normal acetic acid. Yeah. Any other questions? Yeah.
Okay, and with that bottom middle section, and the nerd goes into the carbonyl or whatever.
Yep.
We need to like activate the O.
Good question. I am adding a carbon minus to a carbonyl. Do I need to activate my carbonyl before that reaction? Consensus says yes or no. Why not? If you've got a carbon minus that's a good nucleophile, you do not need to activate your carbonyl, right? And if you're going to activate your carbonyl, I'll use trace acid. What does acid do around Grignards? Acid-base reaction. You can't in this way, right? I can't take a proton because I'd be adding 2 different species. The acid-base reaction would win. Okay. That's how we talk about oxygen as nucleophiles. Now we're going to introduce you to 3 new compounds, imines. Now, imines are formed by taking nitrogen nucleophiles and adding them to our carbonyls. We get what we call a primary imine. What we're talking about there with this primary is the substitution at this nitrogen. Secondary imines, this is where we have 2 groups, and then tertiary, we have 3 things, and usually in these ones we call them iminiums. This is because if you have nitrogen here bound in this way, it's going to have a formal positive charge. You have 4 bonds to it at that same time. These ones here are a cousin of the reactions we've talked about. You take carbonyls plus a nitrogen, and we can form these imines by stripping out water. The reason we introduce these now is because they follow the same general patterns that we've been talking about with acetals. It's just instead of oxygen as your nucleophile, we're now using nitrogen as our nucleophile. In general, in terms of relative stability, imines are not isolated as primary imines. They are actually way more reactive, harder to isolate, because it's really easy to take water and just strip this back, especially a molecule or reaction like this I'm showing you here. What's the state, solid, liquid, gas, of ammonia? Ammonia is what? Solid, liquid, or a gas? It's a gas, right? So if I tried to do this reaction and I have a little bit of water around, this equilibrium will push this way. This one will lose very easily. So just in general, these are molecules we can form, but in terms of relative stability, the full acetals are way more stable than some of these simple imines. In terms of naming, what we have here is imines. This is the name we give to a carbon double oxygen becomes a carbon double nitrogen. Depending on what we bring along to the party, if I have other heteroatoms on here, nitrogen attached to oxygen, it's just an imine. With this OH, we give it a special name. It's called an oxime instead of an imine. If I have two nitrogens attached, that's still an imine core. Nitrogen attack, we call it a hydrazone. I did not write these things. Please do not blame me. I have no idea. But hydrazone, what does it sound like? Back to the other carbonyl compounds. Hydrazone is kind of, if you listen, it sounds like a ketone. Hydrazone. That's where again, they came from. The naming, it's the own part. The naming came because most of these compounds start from ketones with this addition of hydrazine makes a hydrazone. That's at least where the naming convention came in. All of these have the same mechanism. Nitrogen is going to add as your main nucleophile. You're going to end up swapping carbon double oxygen for carbon double nitrogen as you go between the two. So the way that this works, I'm going to start off with a carbonyl and a nitrogen compound. Notice I'm starting off with a primary amine, something where I've got two hydrogens there. When this reaction is done, you're going to end up making water where those are the pieces we're going to be swapping out. Just for sort of keeping track, those are the centers that we're going to have our reaction on. Now when I do this, it is typically done slightly on the acidic side. Most imine formation is just below 7, 4 to 6 is kind of what we do. We'll talk a little bit more about the specificity of that next class. But in terms of mechanism, this is going to start where my nucleophilic nitrogen is going to add directly to my carbonyl. That's going to give me O minus. I've got my R prime, and I've got my new bond, nitrogen, hydrogen, hydrogen, R. Positive charge. Yes?
Why do you activate the carbonyl?
Great question. Why didn't you activate your carbonyl? That is number one question everybody asks. Second one, too, is, dude, you just made an O minus. Isn't that illegal? Right? Is that an O minus? It's not just a normal O minus. This is a special molecule. What's the overall charge of what I just drew? 0. Goose egg. This is a zwitterion. You are fair game. I made a plus, I made a minus. They're separated. This is not the happiest molecule in the world, but it is not the same thing as an oxyanion. So we've got a shortcut. That's one. Second, really good question. Why don't I just protonate my carbonyl first? Again, point part. You may have seen that mechanism where you protonate your carbonyl first, because you have to get there, right? In the end, you need to protonate this negative charge to move forward. We know this. But I would contend this is the most correct energetic representation of what you see in the system. Because why? What is more basic? Nitrogen, like this ammonia, or oxygen? In other words, if I protonate my carbonyl, what is the pK of the positively charged oxygen carbonyl species? Is there at the beginning of class? -9. What's the pKa of a positively charged nitrogen species? So, that's why. Oh, it's like he plans this stuff. Oh, thank you for walking into my trap. This is why. If you have to make that positively charged oxygen species, this equilibrium exists. Rule number 1, your chemistry does not care about your chem draw. Just because you drew it this way does not mean that's where the energetics or the concentration is going to lie. This equilibrium is going to highly favor this species. So I'm not saying that sometimes for our abridged mechanisms, we add this because it gets the job done. But there's two things about this. And again, I am back to the next most common question. But Jason, if I write this on an exam, am I going to get it wrong? It's fine. I don't care. I will take both of them. But I'm just going to be a little pedantic for just a second. This is allowed because protonated oxygen makes a ridiculously high energy species. Very acidic. This is a neutral compound. That's a neutral compound. I didn't make the worst thing in the world. It's still balanced. This is allowed. On the overall energy that you could do, this one wins in terms of a bunch of bad options, honestly. Okay, that's step one. Oh yeah. What we'll do is we will go through the whole junkety chunk at the beginning of next class. But in the end, review this. We'll review the mechanism next class. I'll see you guys. Okay, so I'm going to go through the mechanism of our imine formation. So that's where we're transferring these carbon double bonded oxygen to some carbon double bond nitrogen. The mechanism where we have these other nitrogen groups where the piece that's attached happens to be a heteroatom like an oxygen or nitrogen is really the same. So you just need to know the core mechanism of taking some kind of a primary or secondary amine and doing this addition to the carbonyl. So as I pointed out in class, these reactions involve catalytic acid. It's usually under slightly acidic conditions at this kind of pH 4 to 6, and we'll talk a little bit more about why that pH is super important just after we run through the mechanism. So step one, we've got our nitrogen attacking the carbonyl. Now we do this attack directly. As I mentioned in class, the reasoning behind this is because nitrogen is pretty nucleophilic. It's not too bad. Second, when we attack with the nitrogen, we're not making a typical oxyanion. We're making a zwitterion. So we have both negative and positive charge in the molecule. It's isoelectric, so it's not quite as high of a penalty as your normal oxygen minus only would be, kind of like what we saw with the cyanide addition. So this is a allowable or a relatively stabilized intermediate. Now if we go forward from here, you notice that what we have to do in the end is we're trying to get to something where I have to get rid of this positive charge and I have to get rid of this negative charge. That involves really adding a positive charge here, so I have to add a proton, and I have to remove a proton from here. Do not, please, 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 do not do this internal sort of thing. When you're saying this explicitly, yes, it's efficient. You're saying, well, I've got a negative charge here, I've got a positive charge over here. It feels just very expedient to say, well, I'll just grab a proton from there. The problem with that is that requires you to have a 1, 2, 3, 4-membered ring. You have 4 atoms there in a line, and the geography is not set up properly to just simply pick off this proton this way. These are discrete events with 2 different transition states. You actually break them up into 2 individual events. So we're going to say that's where we have our catalytic proton. I'm going to just say a proton is in solution. This could be associated with the solvent. You could draw this as it's protonating, let's say, the amine. If you look at this system, right, if I'm at pH 6 and I've got this amine present, the most likely sort of holder, or the most likely repository of those protons is probably my ammonium center. So much like we talked about in the cyanide addition, where you have both the conjugate acid and the base that are part of some equilibrium, here in solution you've got the base and conjugate acid form of some acid-base equilibrium where we're using both of them at different times in the mechanism. So now that we've got sort of this as our proton carrier, we're going to pick off that proton. That's going to give me, again, by equilibrium, I'm going to have my proton exchange This might be a little bit uphill because now we've gotten rid of the negative charge, but we haven't dealt with the positive charge yet. Like this. And as a result of that, my amine is now neutral. So that's going to do the other side of this, where it can now reform that acid catalyst. We can pick off the proton that we need from this center. And that's going to give me my R double prime OH, and now NHR and R prime, where once again, just to complete the pieces, you've got your nitrogen now positively charged. So that becomes the charge carrier, or the catalyst carrier for the rest of the next cycle. So this is halfway. This looks most similar to a hemiacetal, right? You've gone from this carbonyl to now this 2 sigma bonds. The only difference with the hemiacetal is we have a carbon-oxygen bond. Here we now have this carbon-nitrogen and this carbon-oxygen. So we call it a hemiaminal. Aminal is usually the naming we put to it. It's okay. We're not going to. I'm not going to write it down because we're not going to test you on that. Just for fun, the name of it is an aminal. Okay, to keep going though, we need to complete this, and it's going to follow the same kind of pattern where we need to remove this OH. If you went the other way, right, if we tried to push this back down and eject this, then we're just going back to our starting material. So to move forward, we want that to come down to form a carbon-nitrogen double bond, and we need this to leave in some way. So that's where we're going to have to add a proton back to that OH. So under these conditions, what we've got is our acid catalyst, remember, is still sticking around, so we can use that to activate this group for leaving. We've also got this lone pair here, which will help us to collapse back into the center. So the way I would draw this is where we're going back to a higher energy intermediate. We're going to pick off that proton. Now, that would be an equilibrium. You'd probably draw it as, very unfavorable equilibrium, but still possible. Again, we're just going uphill in energy temporarily to make an activated species. And we're going to have our NHR. And again, why do we protonate the oxygen and not the nitrogen? Well, if we protonated the nitrogen, we're just back to this species. Protonating the nitrogen just drives us back towards where we started. We want to move forward in this mechanism, so the only option is to protonate that oxygen first. So that's going to give us back our deprotonated amine, like that. We're going to use that one later. Now that we've got the species, we're taking our lone pair, driving it down, and ejecting that oxygen. So now we're kicking out water. What that lets us do, that's relatively favorable. We're going to get our R double prime, R prime, double bond R. Oops, let me draw my nitrogen, excuse me. And because we just closed on this, we're going to have still a proton left and a charge. This is special. We're going to see this guy again. This is not an imine. This is an iminium. I-U-M. So the iminium is the positively charged version of the imine. It's the protonated nitrogen center that still has this positive charge associated with it. So the last thing we need to do is deprotonate that center. So that'll give us a relatively favorable equilibrium. We're picking off the iminium is actually a fairly acidic center. So our final product here is going to be our just regular imine. Sorry, like this, and R group. So that's now our imine. And this would be, as long as that R group is a carbon, this would be a secondary imine. If it happened to be a proton, it's a primary imine. So just showing this out in good copy, The first step we do here is the addition of our neutral nitrogen to our neutral carbonyl to make us wet ionic intermediate. That intermediate then undergoes a protonation at the oxygen, satisfy that part first. That gives us back the neutral nitrogen or neutral amine, which then deprotonates. So this is one proton transfer step and a second proton transfer step, 1, 2, like this. After that addition, we have our neutral aminal. It's like an acetal or a ketal, but it's an amine alcohol, or an aminal is usually what it's described as, or an N-acetal. I've seen it written as well. Now what we need to do is effectively kick out this OH. We're going to do this by making it to a leaving group by first protonating the center. And again, the equilibrium says it's not super favored, but it's allowable. We're going to protonate this one temporarily, and then elimination of water gives us our carbon double bonded nitrogen, still as protonated. This is a cationic iminium. That's the naming there, where you can see this IUM ending is what's denoting that it's cationic. Last step is we have to protonate the center, so this is where our neutral amine, the proton transfer event, comes back in, deprotonating it through here. So once again, first proton transfer event here, second proton transfer event here, a total of 4 all the way through the entire molecule, giving us this imine, sometimes referred to as what's called a Schiff's base. You may see this in other notations, where what we're saying is as long as that's an R group, especially an aromatic R group, that's given a special name as a Schiff base. So there's one more point I just want to quickly mention about this addition. So if we start off with, let's say, a carbonyl, let's say I've got a methyl and, let's say, tertiary butyl on the other side, right? Now stearic says this is obviously much, much larger, and if I were to do an addition, let's say, of benzylamine, right? So here in a phenyl group onto this, this is going to primarily make, after my acid catalyst, remember the pH here is going to be set to sort of a 4 to 6, slightly acidic, we're going to end up with a single geometry of this product. With my methyl group, so this is the T-butyl center, here's the methyl. And if you notice, what I'm trying to emphasize here is this is a much larger. So the stearics around that center are going to be much greater, and it's going to have a lot of stearic encumbrance. This center here is much smaller. As a result of that, the imine I'm going to form, the geometry I will prefer, is going to be one where the phenyl group is going to sit over on this side. The reason why is, you look at this, there's a possibility of having sort of an EZ isomer kind of situation, right? The other possible geometry I could make would look like this. If I had my methyl, my tertiary butyl, I could have my phenyl group sticking this way. And that generally would lead to a pretty large stearic clash over these two. So this one is less stable, this is far more stable, this is the preferred geometry. And just in general, you see this with the imines. Primarily, stearics will favor the formation of whatever geometry puts the smaller group here near that group, and that way the lone pairs are going to be the ones that are actually closer to the larger group of whatever this is. And this is what you see with both the ketones and aldehydes. You know, if this was a hydrogen, in case of an aldehyde, obviously that's the smaller side, so that helps to sort of dictate it. Now, in certain cases, right, if we had a molecule like this with a methyl and an ethyl, you're going to get both possible products, right? You're going to have the methyl, ethyl, nitrogen R, but also you'll have nitrogen R with the ethyl group here, methyl group there. So in this case, you end up with roughly a 1-to-1 mixture of both the E and Z products, where R group is close to methyl, R group is close to ethyl, and that's just because the physical size, the stearics between both of these two, is not enough to really help you select for one or the other. So there's one more issue that you have to watch. This is how you get with 2 different diastereomers of your imine products that are possible as well. So just going back, the last part I want to do is mention again, and I mentioned it in class, why is it that we do a nucleophilic attack directly on the center? Why don't we instead take our catalytic acid and let's protonate that first? So let's just want to quickly draw that equilibrium. That equilibrium means that what you're preferentially doing is I'm going to protonate that carbonyl, and I'm going to end up with my neutral nitrogen. And this is sort of what we described at the beginning of class. If I were to protonate this center here, I'm saying that the protons can attack that carbonyl. Remember, the pKa of this is that sort of -9. Comparatively, if I'm saying the proton here will find this imine, make this species, this pKa here is equal to about, oh, sorry, I got it backwards. This is about 9. This is about -2 or so. And again, that was what we reflected, sorry, -7 and about 9 to 10. So that's what we talked about at the beginning of class. This equilibrium very, very certainly lies in favor of the weaker acid and weaker base. Stronger acid, stronger base are on this left side here. So we have the same thing kind of going on in this mechanism. Trying to protonate this carbonyl, this would be, sorry, just double correcting it, it's -7. This is a very, very, very strong acid, and this is a weaker acid. Stability and proton generally will go via this way to make this zwitterionic intermediate. Now again, I know you may have been shown a different mechanism where you protonate that first. That's fine. I will accept both of them as you're going through. What's most important is that you identify each of these proton transfer events and you have this kind of sequencing. I'm more just highlighting, again, a good bookkeeping strategy for something that we will discuss more as we go through this course.